Hello students, welcome back to the classroom point. In our today's class, we are going to discuss the molecular orbital energy level diagrams. In our previous classes, already we have completed the theory concept of the molecular orbital theory. Now, today we shall discuss the molecular orbital energy level diagrams. So, these molecular orbital energy level diagrams are of two types, that is, less than or equals to the 14 electrons molecules is of one category and more than 14 electrons molecules of another category. So let us see the first one. Molecules or ions with less than or equals to 14 electrons. So let's begin with the 1s configuration. This completely shows the energy axis. So let us take here 1s orbital of an atom intermixes, produces two molecular orbitals. These two are molecular orbitals. This is called the bonding molecular orbital and this one is called the anti-bonding molecular orbital. Bonding molecular orbital's energy is less than the atomic orbitals, whereas anti-bonding molecular orbital's energy is more than the atomic orbitals. So this bonding molecular orbital is represented as sigma 1s and this anti-bonding molecular orbital is represented as the sigma star 1s. Now let us take the 2s combination. This is sigma 2s and this is called the sigma star 2s. Now let us take the 2p combination. Two px, 2py and 2pz. Here also 2px, 2py and 2pz. So that in case of the molecules or the molecular ions having less than 14 electrons, first p orbital will be produced. P orbital of pi bond. So this is called the pi 2px, this is pi 2py. This is called a sigma 2pz. And here anti-bonding molecular orbital pi star 2px. This is pi star 2py, whereas the final one is sigma star 2pz. So if you see the molecular orbital's energy axis here, the lowest energy is with the sigma 1s. So let us write down the order. Sigma 1s, next sigma star 1s, next sigma 2s, and here sigma star 2s, and here pi 2px, pi 2py, both are having the same energy, so that we can write down them. Pi 2px equals to pi 2py, next sigma 2pz is less than pi star orbitals now. Pi star 2px equals to pi star 2py is less than sigma star 2pz. So this is applicable only to the molecules or molecular ions with having the less than or equals to 14 electrons. Now let us see the other category, that is molecules or their respective ions having greater than 14 electrons. In this case, diagram is as it is, only these two will shift over. That means pi 2px, pi 2py go to the get the higher energy than the sigma 2pz, and sigma 2pz will be lowered. So rest of these two diagrams are same. That's why I am not drawing again these two. I will draw only this diagram. This is energy axis. Two px, 2py and 2pz. Two px, 2py and 2pz. So when these two intermixes with each other, so first sigma 2pz orbital will be produced. Next, pi 2px and pi 2py. And here these positions are not changed. Pi star orbital's position and sigma star orbital position is not changed. Pi star 2px, pi star 2py, and here it is sigma star 2pz. So while writing the electronic configuration for these molecules that is having the more than 14 electrons, we need to exchange the position of these two. That means sigma 2pz comes here, pi 2px, pi 2py goes there, and rest everything is same. So that we can write down that sigma 2pz lower than pi 2px equals to pi 2py and remaining pi star orbitals. So whenever we are filling the electrons, first electrons will go to the sigma orbit, sigma 1s orbital. So this filling of electrons into the molecular orbitals follows the above principle, Pauli's exclusion principle and Hund's principle also. So according to those principles only we shall fill these molecular orbitals with electrons. So electrons first will go to the lower energy orbital sigma 1s. Next sigma star 1s. Once this is completely filled, next electrons go to the sigma 2s. Next sigma star 2s. In case of the pi 2px and pi 2py, if only one electron is present, then it may occupy any of these places. If two electrons are present, then one shall occupy the pi 2px and another one is occupying the pi 2py according to the Hund's maximum multiplicity rule, which says that degenerate orbitals must be filled with electron each, one electron each. And once this is completely filled with 4 electrons, then the next set of the electrons will go to the sigma 2pz. So the same sequence shall be followed there also. Now let us take some molecules and we shall see their bond orders and the magnetic momentum and the magnetic nature along with the stability order also. H2 molecule. Total number of electrons in H2 molecule. Total number of electrons equals to only 2 electrons are present. One hydrogen with every hydrogen with a single electron. So the total number of electrons equals to 2 electrons. And here molecular orbital electronic configuration can be written as these 2 electrons will go into the sigma 1s orbital. So its electronic configuration is sigma 1s2. Then bond order. Bond order equals to half of the number of bonding electrons minus number of anti-bonding electrons. So that gives the half of bonding electrons. 2 electrons are there, anti-bonding electrons are not there, so that it is equals to 1. That means there is a single bond between the 2 hydrogen atoms, and here both of the electrons are paired electrons, hence H2 is a diamagnetic in nature. Let us take the H2 plus. H2 plus means only one electron is present. So total number of electrons equals to only one electron. So molecular orbital electronic configuration is sigma 1s1, whereas bond order is equals to half of number of bonding electrons minus number of anti-bonding electron, that equals to half of 1 minus 0, that equals to 1 by 2. That means 0.5 bond order is present. That means bond is partially started forming. And magnetic moment, since here one unpaired electron is present, the molecule is the ion is paramagnetic. Next, let us see the H2 minus. Total number of electrons. Equals to, each hydrogen contributes 1 electron, so that 2 hydrogens give the totally 2 electrons. Extra negative charge is present, so that total number of electrons in this molecular ion is 3 electrons. So let us write down the molecular orbital electronic configuration. Sigma 1s2, which is completely filled, still 1 electron is present. That goes to the sigma star orbital, sigma star 1s1. So that bond order now is equals to half of bonding electrons 2 are there, anti-bonding electron 1 is there, so that final bond order equals to 0.5. Since 1 electron is present, it is also paramagnetic in nature. Now we shall see that stability usually directly proportional to the bond order. If bond order is same, then it inversely proportional to the number of electrons in anti-bonding molecular orbitals. If anti-bonding orbital electrons increase, then stability gradually decreases. If anti-bonding electrons remain same, then bond order depends. So mainly depends on the bond order. If bond order is same, then we need to consider the number of anti-bonding electrons. So that now let us check this. First of all, the order is bond length. So bond length, again here I will give the bond length is inversely proportional to the bond order. Higher the bond order, lower the bond length. So now let us go for these orders. Bond length, so bond length, if you see this, all these three, H2 plus bond order is same, H2 minus bond order is also same. So both of these are having the similar bond order. When bond order is same, then stability or the bond length depends on the number of anti-bonding molecular orbital electrons. So in the case of H2 plus, anti-bonding electrons are 0, but in this case one anti-bonding electron is present. That means it causes the repulsion, which causes the increase in the bond length, so that H2 minus bond length is more than the H2 plus, which is more than the H2. Next, bond enthalpy. Higher the bond order, more the bond enthalpy. So that here bond order is more for the H2, so its bond enthalpy is also higher. H2 is greater than. Next, H2 plus H2 minus same bond order is present. In such cases, lower the number of anti-bonding molecular orbitals, more will be the stability and more the bond enthalpy. So that H2 plus bond enthalpy is more than the H2 minus. Next, bond order. Bond order is highest for the H2, one bond, remaining two or half of bonds are there. So that H2 is greater than H2 plus, which is equals to H2 minus. Bond order is similar. So now let us take the He2 molecule, whether it exists or not. Total number of electrons equals to 4. Molecular orbital electronic configuration, sigma 1s2, sigma star 1s2. Bond order, half of bonding electrons minus anti-bonding electrons, 0. That means He2 doesn't exist. There is no bond. Now let us see the He2 plus. Total number of electrons, 3. Molecular orbital electronic configuration, sigma 1s2, sigma star 1s1. Bond order, half of the bonding electrons minus anti-bonding electrons. That means in comparison to He2, at least there is a chance for the formation of the half the bond in the He2 plus ion. And what about its nature? It is paramagnetic. Sixth one, He2 minus. Total number of electrons, 5 are present, and molecular orbital electronic configuration sigma 1s2, sigma star 1s2, sigma 2s1. Bond order, half of the bonding electrons 3 are there, anti-bonding electrons 2 are there. So here also bond order is 0.5. Since unpaired electron is present, it is also paramagnetic in nature. Now, if you compare the stability of these ions with that ion, let us take the H2 plus, He2 minus. Let us write down the bond order. H2 plus bond order is 0.5. He2 minus bond order is also 0.5. Number of bonding electrons. In case of the H2 plus, only one bonding electron is present. He2 minus 2 plus 1, 3 bonding electrons are there. Number of anti-bonding electrons. So number of anti-bonding electrons, there is 0. In case of He2 minus 2 anti-bonding electrons are there. If you see the difference between the bonding electrons to the anti-bonding electrons, 1 minus 0, so 1, 3 minus 2 is equals to 1. So the difference value here and here both are same. That means when the difference values are same, both H2 plus and H2 minus has same bond length and bond dissociation enthalpy. So this is the way we can compare these molecules. Now let us take some more molecules. Next molecule, Li2. Total number of electrons equals to 6. So molecular orbital electronic configuration, sigma 1s2, sigma star 1s2, sigma 2s2, 6 electrons completed. Bond order equals to half of bonding electrons 4, anti-bonding electrons 2. That means bond order is 1. So that there is a single bond between the 2 lithium atoms in a molecule. So that lithium is a metal. So the question arises whether it exists or not. Practically it was proved that Li2 molecule, Li2 exists in vapor phase. Since all electrons are paired, we can write down it is a diamagnetic. Next one, let us take Be2. Total number of electrons 4 plus 4 equals to 8 electrons are present, and molecular orbital electronic configuration is sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2. So that bond order, without calculation also we can see that when the number of bonding electrons, anti-bonding electrons are equal means bond order is 0. So that half of the, here 4 minus 4 equals to 0. That means Bu2 doesn't exist. Next molecule, boron. B2 molecule. Total number of electrons are equals to 10 electrons. Molecular orbital electronic configuration, sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, pi 2px1 equals to pi 2py1. You can see that these are 8 plus 2, 10 electrons. So unpaired electrons are present. So it is a paramagnetic. And bond order equals to half of the bonding electrons. So that these 1s, sigma 1s, sigma star 1s usually called the KK shells, closed shells. So that is not required every time because anyhow they get cancelled out. We can take the remaining electrons. So bonding electrons 2 plus 2, 4. Here 2 electrons are there. So that bond order is equals to 2 by 2 equals to 1. So there is a single bond between the two boron atoms. Now let us have the comparison between the H2, Li2 and B2 molecules. So first of all, let us write down their electronic configuration once again. H2, Li2 and B2. Total number of electrons. Here 2 electrons, 6 electrons, here 10 electrons are there. So molecular orbital electronic configuration, sigma 1s2. This is sigma 1s2, sigma star 1s2, sigma 2s2. And in this case directly I am starting from here, sigma 2s2, sigma star 2s2, pi 2px1 equals to pi 2py1. So number of bonding electrons, here only 2 electrons are there. Here 2 plus 2, 4 electrons are there. Here 2 plus 2, 4 plus this one, 6 electrons are there. Number of anti-bonding electrons. Anti-bonding electrons in this case 0. And lithium molecule 2 anti-bonding electrons are there. And boron molecule 2 plus 2, 4 anti-bonding electrons are there. What about their bond order? H2 molecule bond order is 1, Li2 1, B2 also 1. So now let us write down the bond order. H2 equals to Li2 equals to B2 molecule. Then when it comes to the bond length basically depends on the size of the atom. If size of the atoms are similar, then depends on the anti-bonding molecular orbital electrons. So that size of the lithium is greater than the boron. Boron is greater than the hydrogen. Then bond enthalpy. So smaller the bond length, higher the bond enthalpy. Here we purely depends on the size of the atom. So hydrogen size is smaller, so that higher bond enthalpy. Next boron Next one is Li2. So this is the comparison between the H2 molecule, Li2 molecule as well as the B2 molecule. Now let us see the other molecules. C2 molecule. Total number of electrons equals to 12 electrons. Molecular orbital electronic configuration sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, pi 2px and pi 2py. If you say already 8 electrons completed, so that 2 plus 2 4, 8 plus 4 equals 12 electrons completed, and no unpaired electrons, so it is a diamagnetic in nature. When it comes to the bond order, number of bonding electrons, let us cancel these two, so that 2, 4, 6 are there. Anti-bonding electrons only 2 are there. 4 by 2 equals to 2. So there is a double bond between the two carbon atoms in the C2 molecule. Interesting thing is, these 2 electrons, whatever the bond order is coming from the only pi orbital electrons. Why? Because starting last electrons only 2 are there. So that will create the 2 bonds. Hence it was considered that C2 molecule has 2 pi bonds and no sigma bond. And C2 molecule do exist. It exists in vapor state. Let us take the next molecule, N2. So N2 is having total number of electrons 14. Molecular orbital electronic configuration sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, pi 2px2, pi 2py2, sigma 2pz2. So the total is equals to 14 electrons over, and it is a diamagnetic. Bond order, half of bonding electrons minus anti-bonding electrons. So bonding electrons 2, 4, 6, 8. Anti-bonding electrons only 2 are there. So that it is 6 by 2 equals to 3. There is a triple bond between the 2 nitrogen atoms in the N2 molecule. 12th one. Let us take N2 plus ion. So N2 plus means N2 molecule lost 1 electron, so that out of 14, now 13 electrons are present. So molecular orbital electronic configuration, everything not necessary to write down. We have to remove 1 electron from here. Remaining everything is same. So that I am writing from here sigma 2s2, sigma star 2s2, pi 2px2, pi 2py2 and sigma 2pz1. Since 1 electron is present, it is paramagnetic. Bond order, half of. See, 1 bonding electron was removed. Anti-bonding electrons, no change. So that we can write down the 7 minus 2. 5 by 2 equals to 2.5. Is the bond order in N2 plus molecular ion. Next, 13. N2 minus. N2 minus means extra electron we have to add, so that it is equals to total number of electrons 15 electrons. So now molecular orbital electronic configuration, it follows the more than 14 electrons series. So that I'll write down the complete electronic configuration: sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, sigma 2pz2, pi 2px2, pi 2py2, pi star 2px1 equals to pi star 2py0. So that 1, 2, 3, 4, 5, 6, 7. 7 to the 14 plus 1. 15 electrons are there. Here 1 electron is present. So it is a paramagnetic. Then bond order is equals to half of the bonding electrons. Now let us cancel these two. 2, 4, 6, 8. Anti-bonding electrons 3 are there. It is 2.5. Now let us make a series. Orders between the N2, N2 plus and N2 minus. So comparison. Of N2, N2 plus, N2 minus. First of all, bond order comparison. Highest bond order is with N2 molecule, so that we can write down that N2 is greater than. These two are having the same bond order, so that we can write down that N2 plus equals to N2 minus. Bond length. Lower the bond order, higher the bond length. Then these two must have the equal bond length. But between these two, wherever less number of anti-bonding electrons are there, that is more stable. That means having the lower bond length. More the anti-bonding electrons, higher the bond length. So that here 3 anti-bonding electrons are there. Here 2 anti-bonding electrons are there. So that bond length is more for N2 minus, next N2 plus, next N2. Bond enthalpy. So bond dissociation enthalpy depends on the bond order. Higher the bond order, more the bond dissociation enthalpy. So that N2 has the highest bond dissociation enthalpy. Next one, N2 plus, N2 minus. More stable is N2 plus because less number of anti-bonding molecular orbital electrons are there, and here more electrons in the anti-bonding molecular orbital, so that N2 is greater than N2 plus, greater than the N2 minus. So this is the order. Now let us see the oxygen molecule. O2 molecule, total number of electrons, 16 electrons are present. Molecular orbital electronic configuration: sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, sigma 2pz2, pi 2px2 equals to pi 2py2, pi star 2px1 equals to pi star 2py1. So that it is equal to 16 electrons. 2, 4, 6, 8, 10 plus 4, 14, 15 and 16 electrons. See here, it is having the unpaired electrons in the pi star anti-bonding molecular orbitals. That's why it is paramagnetic. So this theory is able to explain the paramagnetic behavior of the oxygen molecule, because it says that the presence of unpaired electrons in the pi star orbitals gives the paramagnetic nature to the O2 molecule. Other theories do not explain the paramagnetic nature of the O2 molecule. It is paramagnetic. Bond order equals to half of bonding electrons 2, 4, 6, 8. Anti-bonding electrons 2 plus 2, 4. That means there is a double bond between two oxygen atoms in O2 molecule. O2 plus. From this you have to remove the 1 electron so that it is equals to 15 electrons. So final electronic configuration is, here only I am writing, rest everything is same. Pi star 2px1 is equals to pi star 2py0 because 1 electron was removed. And here also, this is also paramagnetic in nature. Now bond order equals to half of bonding electrons not disturbed 8, anti-bonding electron 1 reduced because 1 lost 2.5, bond order is increased 15, O2 2 plus. That means from here we have to remove the 2 more electrons. So total number of electrons equals to 14 electrons. And molecular orbital electronic configuration, straight away, since from here to here 2 electrons are removed, those 2 electrons are from these pi star orbitals only. So that finally pi star orbitals are with pi star 2px0, pi star 2py0. Since no electrons here, remaining electrons are paired electrons, so it is a diamagnetic. Bond order, half of bonding electrons again not changed, 8 minus earlier 4 anti-bonding electrons, now 2 more removed. That means only 2 anti-bonding electrons are present. 6 by 2 equals to 3. So there is a triple bond in the O2 2 plus, similar to the nitrogen molecule. O2 minus. O2 minus means for this 16 we need to add 1 more electron. That equals to total number of electrons are 17 electrons. So what could be the molecular orbital electronic configuration? Since I am not repeating the common things up to here, everything is similar. Only last electrons I am writing. So that here 16 electrons means these two are common. 1 more electron means extra electron we have to add here. Pi star 2px2 equals to pi star 2py1. Unpaired electron is present, so it is a paramagnetic. Bond order, half of bonding electrons again no change, 8. Anti-bonding electron 1 extra added. That means instead of the 4 we have to take the 5. So this is equals to 8 minus 5, 3 by 2 equals to 1.5. Now let us see the O2 2 minus. This is called the peroxide ion. And this one called as the superoxide ion. So peroxide ion means extra 2 more electrons. Means in addition to the 16 electrons, we need to add the 2 more electrons. So it becomes totally 18 electrons are present. And molecular orbital electronic configuration, that last electrons, add 1 electron here, 1 electron here. So that becomes pi star 2px2 equals to pi star 2py2. So all are paired electrons. So that's why it is a diamagnetic. And what could be the bond order? Bond order equals to half of bonding electrons, again no change, 8 electrons, but anti-bonding electrons here 4 are there. In addition to that 2 more electrons are added here, so it becomes 6. So that says a single bond. Now if you observe one thing in comparison to all these, here antibonding electrons 4, antibonding electrons 3. One antibonding electron if reduced, bond order increased by 0.5. From here to here antibonding electrons 4, antibonding electrons 2, means 2 antibonding electrons are removed. That's why for every 1 electron bond order, for every removal of the antibonding molecular electron, bond order increases by 0.5. So here we remove the 2 electrons. That's why 2 into 0.5 means 1. Plus in addition to the two bonds. That's why here we got the 3 bonds. And what if you add the 1 antibonding electron? When you add the 1 antibonding electron, bond order decreases by 0.5. Here 4, here 5, here 2 is the bond order, here 1.5. Means 1 extra antibonding electron decreases the bond order by 0.5. And from here to here 4 antibonding electrons, here 6 antibonding electrons. For every 1 electron 0.5, so that 2 electrons means 1 bond order reduced. That's why 2 becomes 1 in this case. So it clearly says that the presence of the number of bonding electrons increase the stability and bond order, and the presence of the antibonding molecular orbital electrons decrease the both bond order as well as the stability. Usually bond order is directly proportional to the stability. Let us take those orders also. Comparison. Comparison of O2, O2 plus, O2 2 plus, O2 minus, O2 2 minus. So first let us take the bond order. Highest bond order is with this one, O2 2 plus, 3 bond order. Greater than. Next O2 plus 2.5. Next O2, 2 is the bond order. Next O2 minus 1.5. Last is O2 2 minus 1. Bond length. Higher the bond order, lower the bond length. So that bond length is least for the O2 2 plus, O2 plus, O2, O2 minus, O2 2 minus. Bond order is directly proportional to the stability also. Means stability order also follows this similar order. So this is about the comparison of the O2 plus, O2 and its respective ions. Now let us compare the boron, carbon, nitrogen, oxygen and fluorine, their bond orders as well as the bond enthalpies. These three are formed by 2s 2p mixing, and these are formed without 2s 2p mixing. Let us see the total number of electrons. Here 10, 12, 14, 16 and 18. Write down their molecular orbital electronic configuration. Sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, pi 2px1 equals to pi 2py1. And in this case, sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, pi 2px2 equals to pi 2py2. And here sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2 pi 2px2 equals to pi 2py2 sigma 2pz2, and O2 molecule sigma 1s2 sigma star 1s2 sigma 2s2 sigma star 2s2 sigma 2pz2 pi 2px2 equals to pi 2py2 sigma 2pz2. Sorry. Pi star 2px1 equals to pi star 2py1, and the last one is sigma 1s2 sigma star 1s2 sigma 2s2 sigma star 2s2 sigma 2pz2 pi 2px2 equals to pi 2py2 pi star 2px2 equals to pi star 2py2, because two more electrons are added here. Now let us see their bond orders. In B2 molecule, bond order is 1, that already calculated. C2 molecule 2, N2 molecule 3, O2 molecule 2, and F2 molecule is 1. So usually these bond orders stability follows the bond order and also bond enthalpy. Now let us see the bond order. So bond order is highest for the nitrogen. N2 greater than C2 and O2 both are having the same bond order. C2 is equals to O2 greater than B2 and F2 same bond order. B2 equals to F2. Next, bond length. Bond length depends on the size of the atom. So that here, size of the atom as well as the bond order. Lower the bond order, higher the bond length, and within that same bond order, so larger the size of the atom, more the bond length. Now if you take the boron and the fluorine, their bond orders are only 1. So that these two molecules should have the higher bond length than remaining all. So between boron and fluorine, larger atom is boron. That means boron bond length, B2 bond length is more than the F2 bond length. Next, carbon and oxygen, if you compare that, carbon bond length is more than the O2 bond length. So C2 bond length is more than the O2, and the least bond length is with nitrogen. Next, bond enthalpy. Bond enthalpy depends basically on the number of bond, that means bond order. So that highest bond enthalpy is associated with the nitrogen molecule. Next, bond dissociation enthalpy, what happens if bond orders are same? Now we need to calculate their anti-bonding molecular orbital electrons. So Na I am calculating. Here last orbital electrons I am calculating. Here 0 anti-bonding electrons are there. Here also 0 anti-bonding electrons are there. Here also 0 anti-bonding electrons are there. Here 2 anti-bonding electrons are there. Here 4 anti-bonding electrons are there. So we know that when the number of anti-bonding electrons increase, automatically stability gradually decrease. So between C2 and O2, though their bond orders are same, but anti-bonding electrons are not here. Anti-bonding electrons are here, which makes the O2 molecule less stable than the C2 molecule. That means we need the lesser energy to break this double bond in the O2 molecule than double bond in the C2 molecule. So that bond dissociation enthalpy of the C2 is higher than the O2. Next, when you compare the boron and F2, though they are having the same bond order of 1, but here antibonding electrons are 0, here antibonding electrons are 4 are there. That means boron is more stable than the fluorine molecule. So B2 bond enthalpy is more than the F2. So it looks different. Why? Because usually what we say, higher the bond order, higher will be the bond length, bond dissociation enthalpy. But in these particular cases, when bond order and bond length, bond order is a different order we are following. Bond length is higher for C2 than O2. Bond enthalpy also higher for C2 than O2. So when bond length increases, usually bond enthalpy has to decrease. But in these cases, bond length purely depends on the atomic size. Bond enthalpy depends not only on the bond order but also on the number of antibonding molecular orbital electrons. Now, let us see their magnetic behavior also. What about the B2 molecule? Unpaired electrons are there. So this is paramagnetic in nature. Here, no unpaired electrons. This is diamagnetic in nature. Here, no unpaired electrons. It is diamagnetic in nature. Here, unpaired electrons are there. So, it is a paramagnetic in nature. Again, here, no unpaired electrons. It is diamagnetic in nature. Dear students, I hope you understand this video. If you really understand my video, please do like and share it. Subscribe the channel, and we shall meet in the next class. Thank you one and all.